Okay, it's 1:15, so we'll start. So, good afternoon, everyone. In today's class, we're going to cover, that's wrong, we're not going to cover section 5.1. We just covered section 5.1. We're going to cover sections 5.2 and, wait, is that right? Yeah, 5.2 and 5.3. Double check, let me fix that. 5.2 and 5.3. So office hours today from 3 to 4:30. There's going to be a homework assignment due tonight, and there's another homework that's coming up due on, I think, Tuesday, and we're also going to have quiz 6 today. Okay, so that's on sections 4.3, 4.4, and 5.1. And if you want to see the solution to this kind of warm-up problem that I put on the screen, we had this tube that was 12 centimeters long, and it's got a string wrapped around it 4 times. And the question is, if the circumference of the tube is 4 centimeters and the length of the tube is 12 centimeters, then how do we find out what is the length of the string? And there's a lot of different ways you can approach this problem, but I think the easiest and the most elegant solution is just to make a cut along the length of this tube and flatten it out. If you do that, you'll end up with a rectangle with our string wrapping around kind of like this. 3, oh, I need one more. 4. Okay, well, I didn't draw it very well. But if you do this, then drop a line in each of these sections, you'll recognize that this is length 4, and since we divide this into 4 even pieces, theoretically, if I could draw properly, they're each 3 centimeters long. So each of these triangles is a 3, 4, 5 triangle, and so the length of each piece of string is 5. So you add them all up, and you get 20 centimeters. Oh, I didn't want to put a puzzle on the screen if I wasn't going to solve it for you. So that's a fun one. Maybe I'll put another puzzle on the screen next time we start class. Okay, so let's recall what we were doing last time. So we were learning how to do Riemann sums. So what was a Riemann sum? A Riemann sum was a method by which we hope to approximate an area with a strange shape, right? And the idea was, if we have this area with a strange shape, what we're going to do is fill it up with boxes. And the finer mesh of boxes that we use, the more closely that area is going to represent the true area under that curve. Okay, so we had a few different ways of doing Riemann sums, which the main difference between each method was, okay, I choose a certain number of boxes. Okay, I know they're all going to be a certain width, but how do I choose the height of each box, right? And the height of each box was chosen in one of 4 ways. We either chose the height of the function on the left side of the subinterval, or on the right side of the subinterval, or we picked possibly the highest point in that subinterval or the lowest point in that subinterval. So the advantage of the upper and the lower Riemann sums, where we choose either the highest or the lowest point respectively, is they're guaranteed to give us either an overestimate or an underestimate of that area, which could be very useful. Let me make this full screen. Okay, so that was upper and lower Riemann sums, and then left and right were just, left and right. Not really much to them. So how do we actually compute them? Well, we use basically these formulas, okay? So if you want to memorize something like this, then you can certainly do so, and as long as you know how to apply the formula, you will never go astray. But I would say maybe a more reasonable thing to do is just to remember the mechanism by which we find the width of each rectangle which all of the rectangles will have the same width, and the mechanism by which we choose the height of each rectangle, i.e. upper, lower, left, or right. I think if you remember those, you can probably figure it out by doing some sketching of the picture and try to kind of suss out, okay, how many rectangles I have, and then find the area of each one after you assign it a width and a height. Then just add those up and you'll get the answer. So two different ways of doing it. You can either memorize the formula or you can sort of train yourself on the method. Are there any questions about what we covered last time on Riemann sums? Yeah, Gino.
Some of the formula, I think on the top of here it says fa plus 2 delta x. Does that mean 2 times delta x, or is the second delta x?
No, so this means, so delta x is a quantity. So we multiply it by 2. And delta x is the width of a rectangle. So so we add up certain areas, right? So the first term, this is the height of the first rectangle, okay, which is the height of the function at a plus delta x. That means we move from a, one rectangle's width over to the right, and we check what is the function height at that point. And that tells us then, of course, this is a right Riemann sum, so a plus delta x is the right endpoint of the first subinterval. So that's how we choose that. And then how do we get the right endpoint of the second subinterval? Well, we just move an additional width over. So that's why I put 2 times delta x here. I move 2 rectangle widths over and I check the height. Yeah, so delta x is a quantity. Okay, good question. Any other questions? Yeah, Brenda.
So the main difference between the right and the left Riemann sums, is it based on what side of the interval we start on?
Exactly. So you'll notice that the height of the first rectangle, when we do a right Riemann sum, is a plus delta x. So you imagine that we start at a, and we have our curve, right? And we want to find the area from a to b, right? The question is, how tall should the first rectangle be? On the right Riemann sum, we're going to go to a plus delta x, and we're going to check what is the height of the function there, and then we're going to extend it over to the left, and that's going to be the height of our first rectangle. So that's f of a plus delta x will be this height here. Whereas when I do a left Riemann sum, rather than moving over to the right side of this first subinterval, I just do f of a. Now, if I do f of a, that's not going to give me this height. It's actually going to give me the height on the left side of the first subinterval. So instead of doing a rectangle which would look like that, my rectangle would look like this. So that's the crucial difference. Does that answer your question? Cool. Any other questions before we move on? All right, then we will move on. So let's just really quickly remind ourselves, before we get into the new material, I want to just do this warm-up problem together. Okay, so the following table shows us the rate of sales for books per week for a store. And we are supposed to use an upper sum to estimate the total number of books that are sold over the 10-week period. Okay, so in this situation, they don't give us a graph, they don't give us a function, they just give us a table, right? But we can see what is the rate of sales on the left and right side of each subinterval. Okay, so I think maybe a good way to start this would be to draw a picture and try to understand what's happening here. So we need 2, 4, 6, 8, and 10. And at 0, we're at 50. And then we go 75, that's a bit higher. And then we go 82, that's even higher. And then 93, that's higher still. 140 is a big jump, and then 200 is an even bigger jump. Okay, but I'm trying to fit it on here. Okay, so this is generally what the function looks like, but you don't know really whether it looks like this or whether it just goes like this. You don't really know what the function looks like, but we still want to estimate what is the area under that function. Well, it's exactly telling us what is the height of the function on the right side and on the left side of each subinterval. So on this first subinterval, the height on the left side is 50 and the height on the right side is 75. So if we were to do a left Riemann sum, we would choose the height 50 for this rectangle, and then the height 75 for the next rectangle. And if we were doing a right Riemann sum, the only difference is we would choose the endpoint on the right of each subinterval, and that would be our height for each rectangle. And we're going to get something different if we do one of those. Okay, but our choice is to use an upper sum. Use an upper sum. Now an upper sum says we need to use for each subinterval whatever point that we know of which is the largest for that subinterval. Okay, so the largest point. So for the first subinterval, I'm going to choose the height to be whichever is higher between the function values on the left and the right. In this case, it's the right, so I choose 75 as my first one. And then for the next one, I choose again for the second subinterval, whichever one is higher. Again, it's the one on the right. So I choose 82 as the height of my second rectangle. This one's 82. And then for the third one, again, I'm just going to keep choosing whichever one's bigger. So this one, it turns out that the upper Riemann sum gives us the same thing as the right Riemann sum. This one's 93, and then 140. And then finally, the last one will be 200. Now, all we have to do is find out what the area of all of these guys are, and then that will give us an approximation of the area which is under this curve, right? So I'm just going to take all of those areas and add them up. So the first rectangle has area 75, the second one has area 82, the third one has area 93, then 140, and then 200. So if I just add all these up, I'm going to get an approximation of the area under that curve. Do we all agree with this way of computing the area under this curve? Yeah, Christian?
Multiply it by the rectangle.
Yeah, very good. I made a mistake here, didn't I? I was trying to catch you guys out. The area of each of these rectangles is not just given by the height. We need to multiply the height times the width. And each of these rectangles has width 2. Okay? So what I need to do is multiply each of these by 2 in order to get the actual areas of each of these. Okay, so that's just a common mistake that I often see students make on exams, so I'm trying to warn you about that. So multiply each of those by 2 and we'll get an approximation of this area. Any questions on this warm-up problem? Yeah.
How would it look like using the formula?
How would it look like using the formula? Well, I didn't write down a formula for the upper sum. So the upper sum, you're just going to need to choose. You can't really write down a formula for the upper sum because depending on what function you are taking this Riemann sum of, it might be that the higher points are on the left or the higher points are on the right or in the middle somewhere, right? So for an upper sum, we can't really, I mean, there is a formula which you can use, but it uses some machinery which we don't teach in this class. Yeah.
So let's say like the table wasn't given to us, but like the x values were, and then to find the height, you just plug like the x values into the original function.
Mm-hmm, exactly. Yep. But you would have to choose between, well, is the function value higher on the left or on the right, right? Since we're doing an upper sum for this case. But yes, you're right. Any other questions? Yeah.
And so we did not include 50 in our estimate because we're only including like the highest value on the right.
the highest value for each subinterval, right? So the subinterval which is relevant for the height 50 is the subinterval from 0 to 2. And the higher point happens to be on the right of that subinterval. So exactly, we are not going to use the height 50 for any of our rectangles, even though it's on the table. Okay, so it might be a little bit confusing here because we have 5 rectangles, okay? But in our table, we've got 6 numbers, right? So we need to remember we're just picking one of the numbers for each subinterval. So rather than thinking about having 6 rectangles because I have 6 numbers, what you need to think about is having 5 rectangles because I have 1, 2, 3, 4, 5 subintervals. Okay? All right, so let me jump in now and talk about something else. So we're going to spend the rest of this class discussing integration. So we're going to actually introduce today what is an integral. And I'm going to give you the adult version and the less adult version. I won't say child version or baby version. The adult version and the slightly less adult version, okay? So, you know, the adult version is maybe the most mathematically sound and rigorous version, and I'll start with that one. So we call the integral from a to b of f of x dx. We define this to be the limit as n goes to infinity of the sum from I equals 0 to n minus 1 of f of what? X plus I times delta x times delta x. So this is your familiar formula for the left Riemann sums, okay? Well, not with the limit, but this guy. This is the left Riemann sum. So what does it mean when we take a limit as n goes to infinity? Well, n is the number of rectangles which we are going to use, okay? So if we use a steadily increasing number of rectangles to approximate this area, then our picture becomes finer and finer and finer, and the area which we are approximating becomes closer and closer and closer to this thing which we call the integral from a to b of f of x dx. Okay? Which is roughly speaking the area under f of x from x equals a to x equals b. Okay, so we get the adult version and the less adult version. I think the less adult version is helpful for just to intuitively understand what is this integral all about. It's about finding the area under a curve. Now, the adult version tells you how to do that, okay? The adult version says we take a Riemann sum and we allow the number of rectangles to become arbitrarily large, right? And after a while, each step we add one more rectangle, it's barely changing the result, okay? And this limit, you have to, I mean, there's justification needed to say what this limit means and why does it converge and all of these things, but that's sort of outside of the purview of this class. So what it looks like in the end is basically, where did I draw that drawing? Is basically this process, right? We start with big rectangles like these orange ones, right? And then we slowly, we just make the number of rectangles much larger, right? And then when I do this guy and this guy, they give me a little bit better of an approximation of this first little piece of area than does the orange rectangle, right? Because it fills up more of that space. Okay, so the more rectangles we use, the better the approximation gets. And if we do it an infinite number of times, whatever that means, we don't say what it means, but if we do it an infinite number of times, then we're going to get the actual area under the curve. Okay, so a couple things here that I want to point out. Okay, so first of all, notation and terminology. Okay, we call A and B our limits of integration. Or sometimes I'll call them the bounds of integration. Or just the bounds. Okay, so those we call them the limits of integration. And then we also have another word which we use here. The hell? Microsoft Teams decided to update. Okay, there we go. Okay. We also have another word here, which I'll use purple. We call this function the integrand. I know, that's a really kind of a pompous sounding word. The integrand is what we call the function which we are integrating, okay? So, at the end of the day, this writing represents a number, right? It represents the area underneath f of x from a to b. Okay, so when I do an integral using these limits of integration here, okay, when you see these limits of integration here, we know that the end result of this process is just going to be a number. Okay, it will be the area under that curve from a to b. Okay, any questions about this definition so far? So far it's just terminology and notation. Okay, then we're going to go through a couple of rules here. So I've got an extra page here. You don't necessarily have to write all them down, but you should refer back to these notes when you're doing your homework and such like that. So we have some rules about integrals. So let me start with the following. We have that the integral from a to b of a sum of two functions, f of x plus g of x dx, is going to be equal to just the sum of those two integrals on their own. Okay, so we get a linearity rule which looks kind of like the linearity rule for derivatives, right? Derivatives of a sum is the sum of the derivatives. Integral of a sum is the sum of the integrals. Okay, and by extension, since multiplication is nothing but repeated addition, we also get a multiplication rule, right? If we multiply by a constant inside of an integral, we can pull that constant out. Okay, so, and you'll also notice me writing this dx at the end of each of these expressions. And this can sort of be compared with how at the end of each Riemann expression, I get a delta x, right? And now I'm gonna put just the function, and instead of delta x, I'm gonna write dx, okay? And that kind of symbolizes an infinitesimally thin rectangle whose height is f of x and whose width is little dx, which is what we use to describe an extremely small length, basically. Well, you can think of it as an extremely small length. Okay, so in practice, what it means is everything that comes before the dx is the integrand. So it's kind of like the bookend of our integral, okay? The left bookend is the integral sign with our bounds of integration, and then the right bookend is the dx, which tells us when the integrand has stopped. Okay, so another rule that's important to know is that we can switch the bounds of integration and get a nice result, which is that the integral from a to b of f of x dx is going to be equal to the integral from b to a of f of x dx with a minus sign. Okay? So loosely speaking, this is kind of like, okay, if I'm counting area from left to right, then I get the opposite of if I count area from right to left. Okay, so this is sort of synthetic for now. What else do we have? Intermediate bounds. Okay, if I find the integral from a to b of f of x dx, i.e. the area from a to b underneath this function, and I add the area underneath f of x from b to c of f of x dx, then what do you think I'm going to get? If I take a function with 3 points, and first I get this area, and then I add it to this area, then I'm going to get the total area underneath from A to C, right? Add up area from A to B, and then we continue adding from B all the way up to C. Then we're going to get the total area from A to C of f of x dx. And finally, we get the integral of 0 is just 0. Okay? Because the 0 function, what does it look like? It's just a function which is on the x-axis, right? So if you talk about the area underneath something which is on the x-axis, it doesn't make sense because there's no area under it, right? So we just get 0. I mean, it does make perfect sense. The area is 0. Okay. Any questions about these integral rules so far? I know I just threw up a bunch of stuff on the board all at once. Are you overwhelmed? A little overwhelmed. Okay. Well, don't worry. We're going to come back to these several times as we move on. Does anyone have a specific question about any of them that we should discuss before we move on? Yeah, Christian.
Can you just explain the switching bounds a little bit?
Yeah, okay, so loosely speaking, okay, how do I want to give you a satisfactory answer to your question because I think it's a reasonable question to ask. So what do we do when we have a function and we integrate from a to b? What we do, loosely speaking, is we move slowly from left to right and we accumulate area, okay? And then what a and b tell us to do is where to start and where do I stop. Okay, so I think of moving from left to right as the accumulation of area, okay? So if I'm going from left to right, I'm accumulating area like that. But if I'm going from right to left, it's more like I am slowly deleting area as I move from right to left. Okay, so these processes are an undoing of one another. Does that make sense?
Yeah.
That's kind of a not super satisfactory answer. I understand that, but
It's better.
yeah. Okay, so yeah, it's about accumulation of change versus whatever you would assume to be the opposite of the accumulation of change, the unaccumulation or the getting rid of this stuff, right? That's maybe the best, kind of most simplest explanation I can give for that. Any other questions? Yeah.
Yeah, so are there instances where you have to look out for any answers that
we are not going to discuss these things. So it is true, okay, that, okay, if you have a function like, that looks like this, and you try to find the integral from 0 to 1 of 1 over x dx, okay? And you're trying to find this area, basically, right? You can imagine that this area goes up and on forever, and it turns out that this is actually equal to infinity. But we're not going to talk about those things. Every time we do a definite integral with bounds of integration, with like numbers here and here and an integrand, we're always going to get a finite number, and it's always going to be an integrable function. Does that answer your question?
Yeah.
Okay. Any other questions? All right. Then, okay, let's see some examples, because I think this is going to become a lot more clear as we see some examples, okay? So far, we've written down stuff like this, and we've explained what it means, okay? It means the area under this curve from -2 to 4. But we didn't tell you how to actually find out what that area is, other than by approximating it using Riemann sums, right? So later on, we're going to learn some more sophisticated techniques which are going to allow us to find out what this number is exactly. But for now, we're relegated to estimating via Riemann sums. Okay, so let's just do one more example. So I think Annabelle was asking a question about how do I do a Riemann sum when I don't have the table, right? When I just have the function, how do I do the Riemann sum? Okay, and this is how we do it. Well, I think the easiest way is, if you can, try to draw a picture of this function and what you're trying to find out before you start. So we know we're going to go from -2 up to 1, 2, 3, 4. And we're doing the function, the integrand here is 3 to the x. So this is going to represent the area under that curve, 3 to the x, from -2 to 4. So I know if I plug in -2, I'll get 1 over 9. So this is like 1/9. And then it's also going to go through, if I plug in 0, I'm going to get 1, right? So here's 1. And then it's also going to go up to, I don't know, whatever 3 to the 4 is, 81 or something like that. Okay, so this is a function which is going to look like this, right? It's an exponential function, and we are trying to find this area which is trapped underneath it using a Riemann sum. Okay, so we know we need to have 3 rectangles. So here's the 2 things that we need to decide about our rectangles. The first thing is, how wide are our rectangles? Well, if we have 3 rectangles of equal width and their widths add up to 6, right? Then each rectangle has width 2, okay? And that is given by, of course, the same formula that we've been using. Delta x is b minus a over n. Now, our b is our 4, so that's 4 minus -2, and we divide by 3. So that's 6 over 3, which is 2. So we know the width of each rectangle is going to be 2. And now we need to decide how tall is each rectangle going to be. We know we should have a rectangle which goes from -2 to 0, one from 0 to 2, and one from 2 to 4, right? But how tall should it be? Well, the height should be the height of the function on the right-hand side of each subinterval. Okay, so the first subinterval goes from -2 to 0. So its height is going to be whatever the height of the function is on the right side of that first subinterval. Okay, so the first rectangle has height 1 and width 2. Now the second rectangle, I know its base travels from x equals 0 to x equals 2, And the height is supposed to be, again, the height of the function on the right side of that subinterval. So how do I find out what the height of my second rectangle is? I've drawn it on this picture, but how do I know what the height is? The question is, what is this height that is highlighted in green? How can I find out what it is?
You plug it into the function.
Yeah, is that what you were going to say, Annabelle? Yeah, we just take the x value and we plug it in to the function, 3 to the x. So the x value is 2, so it's 3 squared, right? Times the width of that rectangle is 2. And then finally, the final rectangle, it has height 3 to the 4. And its width is 2. So I take these three numbers and I add them up, and that tells me what is the area of these three rectangles added together. And that gives me an approximation of the red area, right? It's not a great approximation because look at all this stuff here, right? All of this stuff here is like extra area, which we are counting, which we shouldn't have counted. So that's why it's an approximation and not an exact representation. Any questions about this example? Okay. I know we're doing a lot of Riemann sum examples, but I think it's important to see a lot of them because they're a little bit unintuitive at first. Yeah.
So integration is Riemann sum?
I wouldn't go so far as to say integration is a Riemann sum. I would say that integration is the limit of an infinite number of Riemann sums, right? So say we were to refine our mesh, okay? And now I'm going to use rectangles which look like this. You can see how the error becomes less, right? If I were to use a more sophisticated technique, right? Using these red ones, then look at all of this stuff. This stuff and this stuff and this stuff was extra error, right, from the green mesh. And when I refined to the red mesh, I got less error, right? So you can imagine if I used even skinnier rectangles, it would get better. And if I used even skinnier and skinnier and skinnier and skinnier rectangles, then the area would become really, really close to the true area. So in that sense, yes, integration can be viewed as the limit of this process, but that statement is sort of vacuous because we haven't really discussed what limits are in this class. So yeah, I just got to do my best with with what we've got with this book. So does that answer your question? Okay. Sorry I can't give you a more specific answer. If you come to office hours, maybe we can talk more about it. Okay, any other questions specifically about this problem? Okay, then let's move on. So I want to make sure that I have time to talk about .3. And specifically, 5.3. Okay, so we've kind of mentioned so far that if we were to do the integral from a to b, okay, then we just take this function and we check what is the area underneath it. And by underneath it, we meant between it and the x-axis, right? We just want to count up what is that area, right? But what I've not said so far is what happens if the function goes beneath the x-axis, right? If we go beneath the x-axis, then the idea of saying what is the, quote, area under the curve doesn't really have a meaning, right? Because underneath is just like a bottomless pit, right? So we need to sort of adjust our definition here a little bit, okay, to account for this circumstance, right? But if we think of f of x as being a rate of change, right, then when the rate of change is positive, as we move from left to right, we can visualize that we are sort of accumulating whatever this is a rate of change of. So if this is a rate of a change of a substance, then as we move with positive rate of change, that means I have like positive velocity, right? Or something like that. Then as I move forward, I accumulate distance, right? But if my rate of change becomes negative, right? If my rate of change of my substance becomes negative, then as I propagate this, then what's going to happen is when the rate of change of my substance is negative, I'm not accumulating that substance, I am getting rid of that substance, right? So that's like if I had negative velocity, I'd be moving in the opposite direction, so my distance from wherever I started is decreasing. So the way we think about this in terms of our integral is to say that we consider this area as sort of negative area. And what I mean by that is that the integral from a to b of f of x dx is going to be equal to the area above the x-axis whatever that may be. So we count up all the area which is above the x-axis, and we are going to subtract from that the area beneath the x-axis. Okay, and this gives a more complete picture of how integration works. So now we can handle functions that are above the x-axis, and we can handle functions which pass beneath the x-axis, and we can handle functions which do both, right? Sometimes this function is above and sometimes it's below. So all we're going to do for this one, if we were going to take, for this example, we would get that the integral from a to b of f of x dx is equal to 1 minus 3. So we actually get a negative number. That's perfectly fine, because remember, integrals are about the accumulation of change, right? It's possible for us to accumulate a negative change, right? i.e., I could be moving backwards, or I could be losing money, or I could be getting rid of a drug in my bloodstream, or I could be, anything that could be decreasing, right? We want to say something about, well, what was the total change of that substance over an interval? And if that total change happened to be a decrease, then we'll get a negative number. Any questions about this expanded definition for the integral here? Okay, by the way, it still works with Riemann sums, okay, because of course, if you were to take a rectangle like this, when you do f of, say this point is like xi. If you do f of xi times delta x, what am I going to get? F of xi is a negative number, and I multiply it times the width of that rectangle, which gives me the area of this rectangle, but negative. So the Riemann sum structure still applies here as well. Any questions about this before we see a lot of examples? You feel okay about this? Let's have some thumbs. How are we feeling about integrals as area so far? Thumbs up if we're kind of happy with this definition. Thumbs down if I'm confused. Okay. That's looking pretty good. I think it'll become a lot more clear when we do some examples. So let's move on and let's try problem number 2. We're going to see a ton of examples here. So we have integral from 0 to 2, integral from 2 to 3, integral from 0 to 3, and we're given this picture of what the function looks like and what are each of the areas which are trapped by the curve and the x-axis. Okay, so all of the area which is above the x-axis, we are going to accumulate, okay, as positive area. And then when we accumulate negative area, we're just going to subtract it from what we get. So let's start with the first one. I want to do the integral from 0 to 2. So my bounds of integration go from 0 to 2. So I want to find the area above the x-axis minus the area beneath the x-axis when I consider the function over this small interval. So for this example, for the bounds of integration which we have in part A, there's no part of the function which goes beneath the x-axis. So I have all positive area, right? So in this case, this represents the area underneath the curve from 0 to 2, which is exactly visualized here with green. And it's given by just whatever that area is. It's marked on the thing. We get 2.5. Questions on the first one? All right, let's make it more complicated. Let's do the integral from 2 to 3. Well, I want to find the area above the x-axis minus the area beneath the x-axis when I go from 2 to 3. So what am I going to get for this one? Am I going to get a positive number or a negative number here? Negative, right? Because the area is beneath the x-axis. So I'm just going to take whatever that area is and make it negative, and that's going to be my answer. Okay. Now how about the next one? Now we're going to go from 0 to 3. Can you see that? We're going to go from 0 to 3. So we start at 0, we count area, 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 and then we get some negative area, and we stop counting once we get to 3. So what am I going to get in this case? Still a positive number, because the number here is going to outweigh the negative area which I accumulate. So it's just going to be equal to, because of our rule, we take whatever the area is above the x-axis and we subtract from that the total area which is beneath the x-axis, which is 0.75. So if we do that, I believe we get 1.25. No, we don't. We get 1.75. The hell am I doing? Okay. So this was the first one which really incorporated both positive and negative area. So let's pause. Have I lost anyone with this area here totaling up to 1.75? I took the area which was above and I subtracted the area which was beneath. Any questions? Yeah.
So what if you had area above and area below the axis in one interval? Would you treat it as the same way as you did with this, with part C, where you would subtract the area of the top interval, or the area of the bottom interval from the area above the top?
Yeah, exactly. I mean, we did the interval from 0 to 3. So this was our interval. So I think that classifies as what you were describing. We have a function whose over this interval it's sometimes positive, sometimes negative. All we did was we took the negative area and we subtracted it from the positive area. Okay, so I mean, you might as well ignore the fact that there's a 1 and a 2 here. We're just going from 0 to 3, right? Okay. Let's do another one. Integral from 0 to 4. Okay, this one's really confusing because guess what? We start at 0 and we accumulate some positive area and then we get some negative area, but then we keep going and we have more positive area. How am I going to deal with that?
Add the two positive areas and subtract them.
You got it. I'm going to add the two positive areas first. So I'm going to do 2.5. I'm going to add that to 2, right? Because this says area above the x-axis. That's counting both of these guys, right? So I can do 2.5, I add 2, that's the area above, and I subtract the area beneath, which is 0.75. Okay, so I get 4.5 minus 0.75, which is 3.75. Okay, and now we're going to get even more complicated. We've got area above, area below, area above, and then again area below. So I'm going to do this one, and you tell me if I did it right or if I made a mistake. So I know that it's going to be the area above minus the area below. So I'm going to do it like this. The area above is going to be 2.5, and I'm going to add 2. Okay, so that takes care of these two pieces. And then I'm going to subtract the area beneath, which is just 0.75 plus 1. So I get 4.5 minus 1.75. No, I don't. I get 4.5 minus 4.5 plus 1/4, which is 4.75. We happy? No, what did I miss? How did I make a mistake here? How could I fix that? The plus, there's something wrong with the plus 1. Okay, I was trying to say that I should add these two things together before I subtract them from the top area, right? If I add two things together and I should do it before all the extra stuff, then by PEMDAS, what I need to have is parentheses here, right? If I put those parentheses there, then I'm going to get the correct total amount of lower area. So I should have used parentheses, which would modify this. I would instead get minus 1.75, right? I even tried to accidentally do it correctly when I was trying to make a mistake. Okay, so that's 3.75 minus 1 is 2.75. Okay, so that's about as complicated as it gets, right? We got area above in multiple places. We've got area beneath in multiple places. All we have to do is just find out what is the total area above, what is the total area beneath, and subtract. How do we feel about that? Any questions on this example? Okay, one final thing to discuss today, and then we'll have our quiz. So the final thing I want to discuss is how to find the area between two functions. Okay, how do I find the area between two functions? So, say I have a function f of x, and I have another function g of x, which is smaller than f of x, on some interval from a to b. And I want to find not the area underneath one of these two curves, but the area which is precisely between the two. Okay, so that's this area which is seen in green. Okay, so all I'm going to do for this one is use some information which I've already learned, which is namely, I already know how to find the area which is underneath f of x, right? And I also know how to find the area which is beneath g of x, right? I've learned those two things. So is there a way I can combine this information in order to find out what is the area between these two curves? Yeah, I can subtract the two, right? If I put this one on top, then I can see that the area that I want is exactly what I get when I take the larger area and I subtract from it the smaller area. Okay, now for the green, I know the green is given by the integral from a to b of f of x dx. And I know that the red area, which I don't want to count, actually I want to subtract it, is integral from a to b of g of x dx. Okay, so that's shown here. And then the green is, of course, the area, the total area here. So if I take those two areas and I subtract them from one another, then I get the area between is given by the integral from a to b of f of x dx, and I'm just going to take away the other area, integral from a to b of g of x dx. Now, we learned one of our integral rules, which said actually that we can, if we have a sum or a difference, right, of two integrals, it can be written as the integral of the sum or the difference, and vice versa. So this is actually also equal to the integral from a to b of the function I get if I take those two functions and subtract them from one another. Okay? So, I mean, as of right now, it'd be kind of a pain in the butt for me to ask you to estimate the area between two curves, just because you would have to estimate the area underneath f using a Riemann sum, and then you'd have to estimate the area underneath g using a Riemann sum, and then you'd have to subtract. It'd just be a lot of work. So we probably won't do an example of that. But this is just a further extension of what we have sort of already been discussing here. So are there any questions about this kind of new way of thinking about the area between two curves? Yeah.
So is the function or the equation you wrote down saying that, you take the integral, within the boundary points a, or within, within the interval a, b for f of x minus g of x?
Exactly.
On the right side?
Because this function is actually a new function, right? If I take two functions and subtract them, I'm going to get a new function whose height is whatever height f is minus the height of g. So this would be the new height of our function. So I would put it down here like this. You see what I mean? So it's just a new function which I get by subtracting their heights. Okay. I hear everyone packing up, so I guess it's time for the quiz. I've probably given you enough new info for today. So, okay, let's pack up all of our things except for a pencil and, if you want, a calculator. As long as it's not a graphing calculator. And if you got a hat, please just turn it backwards. If you have an Apple Watch or another smart device anywhere on your body, then please take it off and put it away in your book bag. All of your notes and documents as well. And please also close your book bag so that one could not see into them. 1, 2, 3, 4, 5. Please leave the quiz face down on your desk until everyone has one. And then back to. Sorry, did we miss one? We good? Okay. Okay, everyone has a quiz, right? All right, you ready to just raise your hand if you have a question.